Hello and welcome back. Today we're going to talk about a mixed design ANOVA. Um, it's a very similar test to what we've done in the past as far as independent measures ANOVA, and a repeated measures ANOVA is what we did after that. And it's kind of a combination of the two of those things. Um, so what is it? What can it do? Well, what it can do is test for differences between two or more independent groups while we subject a group of the subjects to repeated measures. So within person design, where they all experience the same conditions and them they themselves act as a control. And this a special interest of what we're doing here is looking at interaction effects. So that's another thing that I can do is look at the interactions between different levels of the factors. So when should you use it? I would say the most important reason, as far as when you should use it, if you are interested in those interactions. So how does it work? Well, um, basically the minor difference is that we have another addition to the partitioning of the sum of squares. So when we have a multiple ANOVA, we're looking at between, within, and then we're also looking at interaction sum of squares. So basically the sum of squares are partitioned into within, sum of squares error, and the interaction. So that's kind of what's operating behind the scenes. And as far as assumptions go, very similar to things in the past: normality, homogeneity of variance, and sphericity. And if you're running a multi-level model, which we will be running, you don't really have to worry about the final two um, there. And as far as other assumptions go, you're also going to want to have a continuous outcome variable. All right, so let's move into my experimental design here. I'm going to first open a couple packages and bring my data in, and then I will explain my experimental design. So first I'm going to open library easy, the easy package. We're going to use that for the easy ANOVA model. ggplot graphics package, NLME. We're going to open that. We're going to open pastex, which is typically used for different effect size measures, omega squared and other various ones. And we're going to also open reshape. I originally used reshape, and I will talk about that in a little bit, but I didn't necessarily use it in this. And then we're going to open readxl2, and we can leave gplots alone. I was originally going to use that as a graphics package, but I found a better way to do what I wanted to do. So we're going to bring in my data here, and then we're going to view it. So I'm going to talk about my experimental design a little bit. So let's say I'm interested in a couple different variables here. We're looking at support, training, and job. And as far as how the variables break down, we're going to be looking at job as a between person variable and support and training as a within person variable. So obviously I cannot really modulate this. I have a group of 8 participants who are half consultants and half academics. And let's say I'm interested, hey, let's solve the scientist practitioner debate. Who's better? The academics or the consultants, the applied people in the field of IO, industrial organizational psychology. So we're going to put them through a couple training courses, and we're going to have a different levels of support there. And support, I kind of defined as, hey, all these we have 3 different training courses that they all are subjected to again. And support, high, medium, low, refers to a chat bot within the online training and how supportive that chatbot is. So we have a very highly supportive chatbot, one that's kind of average, and then one that's low, it isn't really accessible. And we have 3 different levels of the factor training, which are gamified, self, and course. Course is kind of acts as the baseline. It's just the standard online course. Self, we're talking about a self-directed learning training course, and gamified. There's different rewards and things like that. A traditional gamified approach to an online training course. So those are my 3 variables. And as far as outcome variables go, I'm looking at their test score, just an arbitrary test score that I'm going to administer following all of these different advents. So let's go back here. So first I'm going to want to factor my variables here. We're going to start with job, where I specify my data set, and job, which is my between subjects variable, and we're going to use factor to factor that. Again, specify both of those things, and then labels. I'm going to use C to create a list, consultant and academic, and those are my labels that they will be. And I'm pointing R towards those. And we're going to do the same thing for participant this time, same exact code, except I plugged in participant here, and the labels are a little different. We're going to do PO1 all the way to PO8 as far as participant 1 to participant 8, and we're going to factor that. Now we have support. We're going to create a factor for support, and here are labels. We have 3 levels, high, medium, and low. And now we're going to do training. Again, I plugged in training there as well, and then I plugged in the 3 labels, gamified, self, and course. Going to run that. And now the final factoring line, my final factor is groups, which is essentially my grouping variable here that brought them all in. And essentially what it does is combine these two here. So I'm going to run that, create that as a variable. So what I was talking about before, I kind of imported my data like this as a more user-friendly version. But if you wanted to bring your data in wide ways, is what they call it, where we have all of the different factors across the top, and then you can use the reshape too, and then use melt to reshape the data to your liking, well, to ours liking more so. But I decided to bring it in a more user-friendly version for this video. Alright, so now we're going to run some summary stats. I'm using the by function, typical summary stat package, well, utilizing the summary stat package. And mixed design, specifying my outcome variable here, and I'm going to create a list. And this essentially is going to create a combination of all of the different levels here of each of these different factors. So we have data name support, data name training, data name job. These are all my, sorry, I'm a little under the weather. These are all my variables here. And stat desk basic equals false. So we're going to run that, and as you can see, we're looking at all the different combinations possible. For example, high self-consultant, so we have a consultant, high supportive environment, and a self-taught, and then we're going to be able to look at the means and medians and standard deviations, things like that. So we're going to move on and get a little more of a visual picture as far as what summary stats are going on. So we're going to use the box plot function. It's a very easy way to produce some graphics through ggplot, and we're going to use the outcome variable here in the spot, and then I'm going to do 3 separate box plots for each of my predictor variables, and we're going to specify the data here. So as you can see, they're all pretty comparable as far as their upward bounds go. Our medians are somewhat near each other. We're not going to deem anything significant yet, but this is just a graphical depiction. As compared to each other in here, we find pretty similar means and dispersions, and in comparison to our last one, fairly similar as well. And the final one, we're going to do test score and job, and then specify the data name. As far as consultants and academics go, looks like we have a higher concentration as far as academics are, between 70 and approximately 85 or so. So that's notable to take. That's something to take note of. So now we're going to move on to the easy Anova model, but first we want to do some contrast to set the stage. So we're going to specify 1, 1, -2. We want these equal to 0, as we have stated before. And these are orthogonal contrasts as opposed to the ones later. So we're going to want them to add up to 0. So we're going to do those. And then we're going to do contrast and then create a C-bind in ordered list of mix 1 and mix 2. We're going to do training in this one. Now we're going to do some more contrasts. 1, 1, -2, 1, -1, 0. Same setup. Mix 4, same thing. And then we're going to do contrast, data name, in this case support. We don't have to worry about job because there's only two different levels to that factor, so it naturally goes against itself, if you will. Then we're going to cbind again, mix 3 and 4. All right, now we're going to create the easy model. So we're going to run easy Anova, the easy way to run Anova. Data name, our dependent variable here, our outcome variable rather, is test score, WID. That's essentially, hey, where do we want to get this data from? We want to get it from the participants. Between, this is our between variable there. Within, again, we're looking at training and support, so we're specifying that there. And type 3, we're doing type 3 sum of squares, and that's the reason why we did want the orthogonal contrast. And then we're going to say detailed equals true, which just gives us a little bit more detailed of a report. We're going to run that by just running easy easy model there. And we have our output here, which I will go back to in a couple minutes, and we can talk about interpretations. But as you can see, we have our main effects spanning all the way to our three-way interaction here, as well as our test for sphericity. It's a tough word to say. And again, we're going to come back and interpret those. And now we're going to move on to a multi-level model. A little bit more complex of a way to look at things. So in this case, our contrasts work a little bit differently, where our baseline, where our average, our medium, is going to act like our baseline, and we're going to specify that as 0 in both cases. And in the case of non-orthogonal contrasts, we're not worried about the adding up to 0 as well as the negative versus positive. In this, we're actually going to be comparing the zeros. So we're going to run those and then do the same thing we did before with the cbind, and we're going to specify support for this one. And our next one will be training here. 1, 0, 0. 0 is the baseline. And we're going to actually want to change this. We'll see how that affects things. Again, we want to keep the middle value a constant because it is our baseline. Con 3, contrast 4. Now we're going to bind them together. And we're going to view those. And that allows you to see what comparisons you're making here. So we're going to move on now. So now we're going to create a baseline model, and then we're going to build it from there. So the baseline model, what we're doing is essentially creating an intercept model, and that's the most basic thing. And then from there we add predictors as we go all the way up to the interactions. And basically what we're doing is we're, like I said, creating the intercept here. And by saying random, we're talking about, hey, where do our variables come from? Participant. Training and support, those are within variables. Data equals mixed design, and then method equals ML. And if you are wondering, I guess actually I don't think it pops up in here, but ML stands for the maximum likelihood model. So now we're going to build on this, and what we're going to do is call it model 3, and we're going to use the update function to update our original baseline model. We're going to run that first rather, and then by saying period tilde period, that means keep everything the same as it was before in the baseline model, but we're going to add support as a predictor. And the same thing, keep everything the same, update this, but add job as a predictor. And now we're going to add training as a predictor. The same, and then model 4, add that to training. And now we're going to add the interaction of support and job. Model 7, we're going to add to model 6 and add the interaction between training and job. And we're going to want to add to model 7 here, the interaction of training and support. As you can see through these past lines, through line 64, we're doing all the different combinations of the interactions. And on this one, we're looking at the three-way interaction here. So we're going to do training colon support colon job, and the colon in all of these cases are telling us to look, telling R rather, to look at the interaction. So we're going to add the three-way interaction there. Now we're going to run the Anova, and what we're essentially doing is we're going to compare all the models that we've listed, and we're going to do that by listing them in order: baseline, model 3, model 4, model 5, model 6, model 7, model 8, and model 9. And that produces our output here, p-values and L-ratios. And we're going to summarize that, and this is going to allow us to see the t-values and things of that nature. And we can see the significance of the t-values that we obtained. From a cursory examination, it doesn't look like we have any significance, but nevertheless, we will move on and then go back to interpretations. So if we wanted to view our interactions, we could run the interaction plot here, interaction plot function, mixed design, we're specifying each time. In all of these cases, we're specifying our data, as well as we're listing our variables in no particular order. And if we were interested, we could add job as well. Let's see what that does. For some reason that causes an error, but nevertheless we will move on. Alright, now if we're interested in effect sizes for a specific contrast that we're interested in, we could specify a function here. So we're going to call it R contrast and then create function TDF, and we're telling R in this equation here we want to be able to plug in for T and DF, and then print paste. That's going to print out our value. So now we're going to want to plug in our T and DF values that we have found from our output previously, and we're going to run that, and we get 0.19, which is a small effect size. And the reason I specifically chose this is at the beginning I didn't necessarily mention that in the video, but my hypothesis was specifically interested in this contrast here, which focused on contrast 1. So now I'm going to go back and let's do some interpretation. So as far as our means go, they're fairly straightforward, and it's extremely difficult to interpret them when you have so many different combinations. So I'm going to skip that. So we're more so going to move towards our first ANOVA, our mixed method ANOVA, as opposed to the multi-level one we did. And what we are interested in this case, I guess before we do anything, we're going to want to look at Mauchly's test. And if we look down at our significance values as well as their corrections, we do not have any violations because we have non-significant results. A little counterintuitive, but as far as this assumption goes, we want to achieve non-significance, and we have. So our assumption is met. So now we're going to look at ANOVA, and I guess it would be helpful to start at the bottom, because the highest order interactions, that's basically they make any main effect or lower order interactions negligent. So we're going to start at the bottom, and it looks like from there up we don't have any significant F values. So let's move on. And now we're going to look at our baseline models here and our multi-level model. So I guess we could first look at the Anova output, and we're looking at our most complex model first, and it looks like we don't have any significance, and as we move up we do not have any significance. It looks like model 7 was the closest to being marginally significant. And if we want to look at what model 7 was, looks like the interaction between training and job. So that's something to take note of. But again, no significance achieved. So now we're going to look at our summary output here. And again, three-way interactions, and as we move up, we don't have any significance. And as far as our effect size goes, in the contrast that we were interested in, we specifically have, well, not specifically, but we have a fairly small effect size, as someone expected. And for the purposes of this assignment, which was mentioned in the writing that came with this, another interest of mine was also the main effect of support, no matter what the levels of anything else. And if we look at support, which we already sort of have, the p-value is not significant as well. The main effect was non-significant. And if we want to interpret any of these graphs, most of the interaction plot is what's most important to us, and it doesn't look like we have interactions graphically, which would make sense because numerically we did not have any interactions either. Okie dokie, I think that's about it. I'm gonna go take a nap. Thanks.